In this video, we'll explore anharmonicity and how we can use the Morse oscillator to calculate constants associated with vibrational motion of molecules. First thing to note is, of course, that we've got the functional form for the Morse oscillator given here. In the Morse oscillator, we have a coefficient alpha. And in that coefficient we have K, the force constant, and dE, which represents the depth of the potential well. When we use the Morse potential in the Schrödinger equation, we get an expression for energy shown here. If we take a careful look at this expression, we'll note that the first term is the same as the term that we get for the harmonic oscillator. The second term is a correction factor that accounts for the anharmonicity of the potential. So let's graph the potential. We're given here several factors associated with the hydrogen chloride molecule. So we'll start with a simple graph here just to make sure it looks right. And when we select the graph tool from MathCad, we get this graph here, which clearly shows us nothing except that we do have a sharp rise here on the left-hand side. One of the problems is that the limits of the axes are just not right. If we look down here in the right-hand corner, the upper limit for R is 10, and if we're talking about meters here, that's obviously way too large since the bond length of the molecule itself is on the order of 127 picometers. Clearly we'll need to change that, so let's change it to something on the order of 500 picometers. So here we've entered 5 times 10 to the minus 10 for 500 picometers as the upper limit for the axis. It should be noted that it's also sometimes helpful to re-enter the 0 as the lower limit as well. With the new upper limit, we still don't get a good plot, and that's because the vertical axis limits are not quite right. So to determine an appropriate magnitude for the vertical axis limits, we'll just simply calculate the value of potential at 500 picometers, and we get something on the order of 10 to the minus 19 joules. So we will enter an upper limit on the order of 10 to the minus 18 joules for the vertical axis. And then we'll also retype the 0 for the lower limit, just to be on the safe side. After any of those limits, we get a nice graph that shows typical molecular potential, so we can see that the Morse potential does a pretty good job of mimicking the actual molecular potential. Next we move on to the spacing between energy levels. We'll start with the equation here for the energy of a given level. And then we'll just take the difference between the energies of level n plus 1 and n, in this case, to give us this expression here. And there's actually a mistake there. We'll just erase that. Now, if we compare these terms, we'll certainly see that some terms cancel out in the first harmonic term. And if we then expand the quadratic terms in this equation, this is what we get. We can then take the difference between those two quadratic terms. We get 2n plus 2, which then obviously goes into this equation here at the bottom that corresponds to the spacing between consecutive energy levels. Okay, so let's look at the specific example of carbon monoxide. What we have given here are the fundamental frequency for the transition from 0 to 1 and the first overtone for the transition from 0 to 2. you'll notice that the 0 to 2 transition is almost, but not quite, twice the frequency of the 0 to 1 transition. So here we have the representative energy levels just to show you exactly what these frequencies correspond to. The 0 to 1 is 2143 wave numbers. The 0 to 2 is 4260 wave numbers. And then if we take the difference between these, 0, 2 and 0, 1, we get the difference between the 1 and 2 levels. Now we can use this information to calculate the equilibrium frequency, nu E, of the molecule, and the anharmonicity constant, xc, of the molecule. These equations here, corresponding to the difference between the 0, 1 and the 1, 2 levels, come from the basic equation that we derived above for the spacing between consecutive energy levels. You can verify this on your own. So what we have here are two equations with two unknowns, nu E and xc. So we're going to use those equations to solve for nu E, xc. So this will leave up to you as an exercise in class.